Greetings. My name is Mike Levis, and I'm an instructor with the Mount Hood Ski Patrol Avalanche program. Today's topic is snowpack. Snowpack is the second component of the Avy triangle that affects the potential for an avalanche. Snowpack stability determines if a slope will slide given a trigger. Snowpack stability, as we will learn in this module, is intimately tied to weather and weather history. Weather, both current as well as past weather history, will determine the structure of the snowpack, and the structure will determine snowpack stability and ultimately the potential for an avalanche. So let's get into it. Our main goal in this module is to be able to recognize snowpack structure and determine avalanche risk based on the structure we find on the mountain. To do this, we will look at various layers in the snowpack and discuss what weather factors might have contributed to the specific layering we see. We will discuss snowpack metamorphism and how it impacts stability. Metamorphism means change, so we will look at the factors that cause changes in the snowpack and how these changes affect snowpack stability. We will also discuss how bonding occurs between grains of snow and what factors strengthen or weaken these bonds. Let's begin by discussing some basic properties of the snowpack. A snowpack is a mix of ice grains, air, and water. Grains are bonded to each other to varying degrees to form layers. Adjacent layers are also bonded to each other, forming a sandwich structure of these layers. Before we discuss characteristics of layers, it's important to understand two concepts: cohesion and adhesion. Cohesion is a measure of how well the ice grains within a layer are bonded to each other. Highly cohesive layers are well-defined slabs that will slide as a single unit. Adhesion is a measure of how well a layer sticks to the layers above and below it. Low adhesion means that a layer will slide more easily relative to adjacent layers. So when we look at the characteristics of the snowpack, we will look at the layers and try to assess the density, cohesion, and adhesion of each layer. A dense, highly cohesive layer that has poor adhesion to the layer below it is a formula for a slab avalanche. Before we dive into ice grains, how ice grains bond to each other, let's define some key terms in snow science. Faceting, or faceted ice grains, is a specific kind of ice crystal with very angular sides. These crystals form in snow with a large temperature gradient. Faceted grains generally do not bond well and form layers that are not cohesive. Rounded ice grains are formed in layers with a low temperature gradient. Rounded grains bond well to adjacent grains and generally form cohesive layers. Temperature gradients have a large impact on snow crystal formation. A temperature gradient is defined as the change in temperature from the snow surface to the ground divided by the depth of the snowpack. It is often expressed in degrees C per centimeter. Metamorphosis, as we mentioned before, means change. Metamorphosis in the snowpack refers to changes in the snow crystal structure. These changes can be caused by temperature, pressure, and time, and can increase or decrease snowpack stability. Okay, so let's discuss what makes a snow layer highly cohesive or strong. Generally speaking, rounded snow is stronger than faceted or angular snow. Rounded snow can be formed from faceted snow. Time is our friend in this case. After snowfall, gravity and moderate temperatures, low temperature gradient, will compact the snowpack, converting or metamorphosizing faceted grains into well-bonded rounded grains. So why are rounded grains strong? As we mentioned previously, snow is composed of ice grains, water, and air. At low temperature gradients, water vapor settles in place and freezes between grains. This has the effect of rounding off grains and freezing adjacent grains together in a more cohesive matrix of ice crystals. Snow is dynamic. It changes with time, sometimes becoming stronger and more stable, sometimes becoming weaker. Moderate temperatures, gravity, and time will eventually turn faceted crystals into rounded crystals. Note this thinking is behind the 48 rule on Mount Hood. You should wait 48 hours after a storm before you go skiing. Based on what you know now, you think this is a good rule. We'll discuss that more in class. Also, In continental climates with much colder temperatures, the time for this rounding to occur can be very long, weeks to months. As I mentioned previously, temperature gradient in the snowpack determines the crystal formation of the ice grain. However, temperature gradients can change as snowpack thickness changes and air temperature at the surface of the snowpack changes. As the temperature gradient is reduced, and with moderate temperatures, ice grains in the snowpack degrade to rounded grains, increasing snowpack stability. So moderate temperatures or a thickening increase in the depth of the snowpack. Conversely, as the temperature gradient increases due to decreasing air temperature and thinning snowpack, rounded grains metamorphosize into facetted grains, reducing snowpack stability. Note also that this effect is bidirectional. The snowpack can morph in either direction, increasing or decreasing stability. So here's some cool pictures of facetted crystals. With the sharp edge of these crystals, bonding between adjacent grains is going to be very weak. It's also important to mention that facetted grains tend to be persistent, particularly in colder climates. Think buried depth form. These grain structures can persist for months in cold climates, leading to weak layer failure a long time after the weather event that created the weak layer. Throughout this discussion, we've been referring to temperature gradients and indicated large temperature gradients can lead to facetted ice crystals and layers that are weak. But what exactly is a large temperature gradient? Generally thinking, anything over 1 degree C per 10 centimeters of snow depth leads to facetting. So greater than 1 degree C per 10 centimeters of snow depth leads to facetting. As an example, if we have a 2 degree C difference between the air and a layer 5 centimeters below the surface, the gradient is 4 degrees C per 10 centimeters, well above the threshold for creation of facetted crystals. In general, the air temperature has much more of an impact on temperature gradient than the ground. The snowpack tends to insulate the ground, keeping it at a constant 0 degrees C, 32 degrees Fahrenheit temperature. In this picture, you can see the temperature being measured at different depths in the snow pit to assess the temperature gradient in the snowpack. This slide shows another representation of temperature gradient. As you can see, due to the insulating effect of the snowpack, the temperature at the ground remains around 0 degrees C. The temperature at the surface is determined by the air temperature. Note that the air temperature can change throughout the day and night, so the temperature gradient will change as well. This is known as a diurnal cycle. Also note, as the snowpack settles or new snow falls, the temperature gradient will change. Warming of the snowpack, in particular rapid warming as found in the spring, can lead to a special kind of metamorphism called wet snow metamorphism. In this case, bonds between grains melt, leading to a loss of strength and structure. This leads to slush. In the creation of slush, small grains tend to melt faster than large grains, releasing a large amount of free water. This free water accelerates bond failure between grains, creating yet more slush. In this case, the snowpack may change quickly from a well-bonded, cohesive structure to a poorly bonded, uncohesive layer and create a wet slide avalanche. The opposite is also true. When the temperature drops, liquids in the space between ice grains freeze, binding the ice grains to each other and increasing the stability of the snowpack. These melt-freeze cycles result in a snowpack that varies between stable and unstable as temperature cycles during the day. This is important to understand. It means that a snowpack that was stable in the morning when we started the ski tour may be unstable in the afternoon when we return. So let's shift gears a little bit and talk about another phenomena called surface hoar. Surface hoar, shown in this picture, are facetted grains that form on the surface of the snow. Surface hoar is basically frozen dew. Surface hoar forms on cold, clear nights when the surface becomes colder than the air due to the emission of black body radiation. This causes the water vapor in the air to convert to a solid through a process called sublimation and form ice crystals, frozen dew, on the surface of the snow. Note, wind will destroy surface hoar, so this forms on windless nights. Surface hoar is not really a problem until it's buried. These layers have weak shear strength and when buried form weak layers that easily fail. When buried, they're hard to see in pits and can persist for a long period of time. Surface hoar can be really large. This photo shows some grains of surface hoar in Utah. You can see the glove there for a reference point. These are pretty gigantic grains of surface hoar, and it'd be great to ski through, but once it's buried, it's going to end up being a buried depth hoar that will be a weak layer. And here's an example of that. This slide shows a layer of surface hoar that's been buried under new snow. As you can see, the buried depth hoar forms a weak layer between two more consolidated layers, which is a recipe for a slab avalanche. Excuse me. Another structure we find in the snowpack is crust. Crust can be in several forms. Wind crust, sun crust, rime, and rain crust are some examples. These structures can act as bed surfaces when new snow is deposited onto a crust. Initially, new snow might not have strong adhesion to these bed surfaces, but with melt-freeze cycles, adhesion can improve significantly. There are some snow structures that resist metamorphosis. When these structures are buried by new snow, they often form buried weak layers that can be a source of failure. These buried layers can be very persistent and may last for months after initial formation. Depth hoar we've already talked about. Crust can act as a smooth base on which surfaces can slide. So if you have a crust, the new snow on top of it, until it goes through this melt-freeze cycle, those are going to be distinct layers, and the crust will act as a smooth surface that the cohesive layer above can slide on. Grapple is nature's ball bearing. These layers tend to be weakly bonded and can also act as a weak layer for avalanche formation. This wraps up our discussion of snowpack. Remember, snowpack is made up of layers. The structure of these layers, density, cohesion, and adhesion determines the stability of the snowpack and the likelihood of an avalanche. The structure changes over time and is heavily influenced by temperature cycling, new snow, and time. If you're interested in learning more about snow science, please sign up for Avy 2 when offered next.